So we have only one generalized coordinate, and that's theta, fortunately. So this system is, to get the equation of motion of the system, we only have to look at a very limited number of partials. So let's first take di L by di theta, and I'm just going to write down what the result is. So we have an m h, so we have a term that comes from the kinetic energy that involves the sine of theta. So an m omega h naught L, m omega h naught L, then there's a sine omega t, and then a cos theta, and a theta dot. Yes, and the 1/2 and the 2 cancel, so I just have 1 out in front. That's good. And then there's a term that arises from the partial involving the potential energy, which will be a plus mgl sine theta. So that's the terms. I'll just double check what I have. Yes. So those are the terms involving theta, and we can now also start taking our partial derivative with respect to theta dot. And here again, we'll have multiple terms. So I'm going to pull an ml squared out in front. Well, no, I won't pull that out in front. I'll have an ml squared theta dot. And then this next term will be an m omega h naught L sine omega t sine theta. And that's it, if I've done that correctly. ML theta plus da, 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 da. Yes, that seems to be right. And then d by dt, di L by di theta dot. So now we take our time derivative, ml squared theta double dot. Then we have to be careful here because we're going to end up with 2 terms. So there'll be a plus m omega squared h naught L cos omega t sine theta. And then there will be the next term, which is a plus m omega h naught L sine omega t cos theta, theta dot. Yes. So much more complicated. So to get my equation of motion, it's these terms subtracting di L by di theta. And we can see from these expressions, though, that we get a fortunate cancellation. So this term will cancel exactly that term. So this and this will end up canceling, because remember, it's subtracting this term off. So that our equation of motion then becomes ml squared theta double dot. So that's from here. I'm just going to keep track of each of these terms as I go along. And then a plus m omega squared h naught L cos omega t sine theta, and then minus an mgl sine theta is equal to 0. So I'm going to collect the terms that multiply sine theta. And at the same time, I'm going to divide through by ml squared. So I'll have theta double dot. And how do I want to express this? Yes, that's right. I'll keep the plus sign out front. So the m's will all cancel. And now I'll have things divided by L. So there'll be an omega squared h naught over L cos omega t minus g over L sine theta equal to 0. So this starts to look a little bit more familiar, but recall that the way we had the angle in the original problem, that was our theta. Normally, when we're dealing with just a simple pendulum, we deal with that angle. So if I want to express theta in terms of phi, theta plus phi is equal to pi. So theta is pi minus phi. And I substitute that in here, but that just introduces a negative sign. So I can rewrite this in terms of phi double dot plus g over L minus omega squared h naught over L cos omega t sine phi equal to 0.
Is theta plus phi pi by 2?
No. So this is the angle phi. I was just trying to draw the simple little pendulum that this is the normal angle phi that we use for the pendulum. Sorry for that confusion. No, so that's the angle phi that I'm really using in these expressions. So at this point, we could go ahead and solve this equation. It's a nonlinear equation. But let's do the little sanity check. And let's take this amplitude h naught going to 0. Do we get back what we expect to get back? So if there's no amplitude on the driving force of this pivot, we would have phi double dot plus g over L sine phi equals 0, which is exactly the expression that you would get for the simple pendulum. That's why I wanted to write it in terms of phi so that we could instantly recognize this. That's the pendulum equation. Then we could do small angle approximation and so on. In this situation, that may not be a bad approximation. If we have a driving force here with this shaft, it's hard to predict beforehand if the angle phi is going to be small because of the oscillatory nature of the driving pivot. If this frequency is very small, likely we have just a slightly perturbed pendulum. But as this frequency becomes large, it may pass through a resonance point, in which case the amplitude could get very large. So there are techniques that one could apply here. Hopefully you've done some Fourier series last year and using Fourier series to solve for these differential equations when you have a driving periodic force is a natural technique. But we're not going to do anything more here. It was just to set up this as the example, and then always important to do the sanity check to make sure you get back what you expect.